Okay, so we stopped here. We are on to angular momentum finally. So if you've gotten to the homework and it's started throwing in a symbol with an L and you're like, what in the world? That's angular momentum, okay? So we're getting there. Newton's second law for translational motion can be written two ways, if you remember. Now, this is like translational, so this is stuff we've already done. We wrote as force was equal to like the change of momentum over time. So there was thrown in momentum. And then we also had that, just force, net force is mass times acceleration. Okay, so for rotational, Newton's second law, we said torque was equal to moment of inertia times angular acceleration. So for Newton's second law for rotational, using momentum, we use the symbol L, and that's angular momentum. Okay, so the next net external torque acting on a system is equal to the rate of change of the angular momentum of the system. So you've got torque is equal to the change of angular momentum divided by time. I'm going to show you how this is analogous. This is rotational. Okay. Translational looks like this. So remember, force and torque are like the same. Force is translational, torque is rotational. But they mean sort of the same thing, right? One just has to do with there's a radius involved because we're talking about a circular object, or it's making a circular motion. All right, so angular momentum is I times angular velocity, just like translational momentum is mass times velocity. Remember, moment of inertia is like mass, and then of course angular velocity and translational velocity. All these different symbols, I know. And then you could break it down again where the sum of torque is equal to angular momentum over time, where again you could plug your new equation here for angular momentum in for L. So you could go IW over time. Well, remember that angular velocity over time is equal to angular acceleration. So the equation that we've already had before, but just to prove that it does actually go back to being related to Newton's second law. All right, so conservation of angular momentum. Just know that in a system, there would be a net torque of 0, which means that you could set the initial momentum equal to the final momentum. This is conservation of momentum, just like in chapter 7, just different symbols. Okay, so and this just says that linear momentum and angular momentum cannot be added to the final total momentum because they're different quantities. Okay. So we have an example, thank goodness, right? That kind of helps. So you have this mouse perched at point P, or B, on the rim of a 2-kilogram wagon wheel that rotates freely in a horizontal plane at 1 revolution per second. It crawls on over to point A at the center, and you're going to assume that the mass of the wheel is concentrated at the rim. What is the frequency of rotation in revolutions per, oh gosh, I cannot talk, revolutions per second when the mouse arrives at point A. Okay, so we've got some information here. First, we have that moment of inertia is initially you're talking about the wheel itself and at point B though, okay? And the mouse. So you're just talking about it on this one point. Well, if it's just one particle, then it was just mr squared. Well, why am I doing m plus mr squared? Because you have the mass of the wheel and the mass of the mouse. You have to include both, okay? For the final moment of inertia, you have point A there. Well, in that one, the mass of the mouse doesn't really matter because it's on the axis point. The only thing that it's really feeling at that point is just the wheel. So it's just mr squared. All right, you know the initial velocity is 1 revolution per second, but you want to figure out what the velocity, or they're calling it the frequency. Sometimes it's this W is referred to as frequency. I want to know what the final is. All right, so you set it up like a conservation of momentum equation, just like we did in chapter 7. So you could do I initial angular velocity initial is equal to I final angular velocity final. All right, so we're trying to find that. So you've got 0.1 kilograms plus 2 kilograms radius squared. We don't know what the radius is. Times, let me put this in brackets so you know it's together, times 1 revolution per second is equal to so the mouse has gone to point A, so just the mass of the wheel at that point, 2 kilograms radius squared times this final velocity. All right, so you just got to solve for final velocity. Well, when you multiply this over, what happens to your radius squared? So if you were worried about not having that number, it's fine. It goes away. So basically you have 2.10 times 1 over 2. Well, your kilograms are going to cancel, and you're left with 1.05 revolutions per second. And that's your final velocity. So it's just like solving those ones in chapter 7. All right, we have a couple more slides, and then I think we'll be done. So angular momentum in planetary orbits. All right, so conservation of angular momentum can be used in orbital speeds as well. So it has this example of like a perihelion and an aphelion. So you would have radius, from the sun to that planet. Okay, so it's giving us an example with this. It says at perihelion closest approach to the sun, Earth is 1.47 times 10 to the 8th kilometers from the sun, and it has an orbital speed of 30.3 kilometers per second. And then it goes on to say that the Earth's orbital speed at the aphelion is, or it wants to know what that is. What is Earth's orbital speed? That's what we're trying to find. When it's 1.52 times 10 to the 8th kilometers from the sun. Okay, so we're essentially doing what we did on the last example. Okay, so we've got just a point, like Earth is just a point on this circular motion. So it's just mr squared. And it's actually wanting us to find Earth's orbital speed. So it's wanting us to find v, okay? Like meters per second. And you might go, well, like, okay, we have w. Well, it's okay because we can actually convert between the two by using that. All right, so we've got the same equation as we had before. Oops, final. So we've got mr squared, and then you can take this equation right here and plug it in for w. So VR is equal to mr squared VR. All right, now if you go through and solve for that, okay, what happens as far as the mass is concerned, you're talking about Earth, so it's the same. And your radius ends up canceling in both situations. Oh, no, sorry, not in this situation. What did I do that for? Okay. Let me restate that. So you've got your mass times the radius here. Yeah, that one's being multiplied over, dividing by mr squared, but the radius changes, remember, because you go from 1.47 to 1.52. Okay, so these cancel. This cancels this, and you're left with mrvi over mr final. Yeah, so look at this again really quick. This is where it is messing up here. See this radius right here? It cancels one of those. So take that out. And then take that out. So when you go to solve for that, it's like mRV is equal to mRV. So it's like this. Okay. Sorry about that. All right. So then you've got your masses cancel because they are the same. It's Earth. So you've got 1.47 times 10 to the 8th kilometers times the velocity, which is 30.3 kilometers per second, divided by 1.52 times 10 to the 8th kilometers, which equals your 29.3 kilometers per second. All right, that's your final velocity there. So hopefully I didn't totally mess you up with this thing. Let me kind of restate just so you understand what I'm saying here. This is mr squared over VR is equal to mr squared over VR. And then that'll cancel one of those. and then you don't have to multiply by the radius or anything like that. You'll just divide by mr to the other side. Well, the mass is the same, but those two radiuses aren't. Okay, so hopefully that helps on that one. And then that kind of goes on to, a gyroscope. Gyroscopes are kind of cool. They're used in things like airplanes, submarines, and if we had time, I'd kind of show you using sort of this situation where I have one of these platforms, and if you spin the wheel like that, it'll just keep you at rest. But then if you go through and you put it up, it'll make you spin too. It kind of goes along with those planetary orbit motions and stuff. And like I said, they use them in all kinds of cool things like airplanes and submarines. But there's no calculation with that. So that is the end of chapter 8. Hopefully this helps on those angular momentum